Maximal flow problem. Suppose a water treatment tank wants to pump a maximum amount through pipelines in source nodes S to T. The water network supply is shown. So here, we have, for example, from S to A, we have 6 million tons of water to supply. From S to C, we have 5 million tons of water to supply, and so on. So the next step that we're going to do is to create the possible paths and find the smallest amount and subtract it to one another. So here, the first path that we've created is SABT. From S to A, we have 6 million tons. From A to B, we have 2 million tons. And from B to T, we have 3 million tons. So the smallest one is 2. So now, we are going to subtract 2 from the rest of the paths. So we have 4, 0, and 1. The second possible path that we've made is S, C, D, and T. From S to C, we have 5 million tons. From C to D, we have 7 million tons of water. From D to T, we have 8 million tons. And so, the smallest amount is 5 million tons of water. And now, we have the new path for S, C, D, and T. We have 0, 2, and 3. So for the last and third path, we have SADT. We have from S to A, the new amount is 4 million tons. From A to D, 4 million tons. And from D to T, we have 3 million tons. And we have the smallest amount, 3 million tons, so we will subtract it to one another. So we have 1, 1, and 0. So showing all the subtraction from the network flow, we already have SA, B, and T as 1, 0, 1, and we have from S, C, D, T as 0, 2, 0, and from S, A, D, T, we have 1, 1, and 0. So the last step that we are going to do is to add all the minimum amount of water to supply from each path. So we have 2 plus 5 plus 3 to get 10 million tons of water to supply, which is the maximal flow that will go through the pipelines.
So minimal spanning involves connecting all points of a network together while minimizing the total distance of these connections. So the steps for a minimal spanning is to select any node in the network and then connect this node to the nearest node that minimizes the total distance. Considering all of the nodes are now connected, find and connect the nearest node that is not connected. If there is a tie for the nearest node, select one arbitrarily. A tie means more than one optimal solution, and then repeat the third step. So in our problem, considering node 1 is the starting node, select the arc or path which has the shortest distance to reach for the nearest node. The nearest node from node 1 is the node 2, and between node 3 and 6, node 3 has the shortest arc or path from node 2. And then the same procedure is applied to the rest of the nodes until all the nodes are connected while minimizing the total distance of these connections. We now reach our optimal solution with a total distance of 177.
So this is our figure. So now we will determine the shortest routes from the origin node 1 to the 6th destination. So we will begin the shortest route solution technique by starting at node 1, the origin, and determining the shortest route or time required to get a directly connected node. The three nodes directly connected to node 1, 2, 3, and 4 as shown in the figure. Of these three nodes, the shortest time is 9 hours to node 3. Thus, we have determined our first shortest route from node 1 to 3. We will now refer to node 1 and 3 as the permanent set to indicate that we have found the shortest route to these nodes. Because node 1 has no route to it, it is automatically in the permanent set. So, determine the initial shortest route from the origin node 1 to the closest, which is node 3. So, if you notice the figure that the shortest route to the node 3 is drawn with the heavy line, and the shortest time to node 3, which is 9 hours, is enclosed by a box. The table accompanying the figure describes the process of selecting the shortest route. So the permanent set is shown to contain only node 1. The 3 branches from node 1 are 12, 14, and 13, and this last batch from the minimum time of 9 hours. Next, we will repeat the foregoing step used to determine the shortest route to node 3. So first, we must determine all the nodes directly connected to the nodes in the permanent set, which is node 1 and 3. Nodes 2, 4, and 6 are all directly connected to the nodes 1 and 3 as shown in the figure. So we will determine all the nodes directly connected to the permanent set. So the next step is to determine the shortest route to the 3 nodes, which is 2, 4, and 6 directly connected to the permanent set nodes. There are 2 branches starting from node 1, 12 and 14, and 2 branches from 3, 34 and 36. The branch with the shortest time is to node 2, with a time of 16 hours. So thus, node 2 becomes part of the permanent set. Notice in our computations accompanying in the figure that the time to node 6, which is branch 636, is 31 hours, which is determined by adding the branch 36 time of 22 hours to the shortest route time of 9 hours at node 3. So as we move to the next step, the permanent set consists of node 1, 2, and 3. This indicates that we have found the shortest routes to node 1, 2, and 3. So we must now determine which nodes are directly connected to the permanent set nodes. Node 5 is the only adjacent node not presently connected to the permanent set, so it is connected directly to node 2. In addition, node 4 is now connected directly to node 2 because node 2 has joined the permanent set. 5 branches lead from the permanent set nodes, which is 1, 2, and 3 to their directly connected nodes, as shown in the table which is accompanying the figures. The branch representing the route with the shortest time is 34, with a time of 24 hours. Thus, we have determined the shortest route to node 4, and it joins the permanent set. So have you noticed that the shortest time to node 4, which is 24 hours, is the route from 1 through node 3. The other routes to node 4 from node 1 through node 2 are longer. Therefore, we will not consider them any further as possible routes to node 4. So, to summarize, the shortest roads to node 1, 2, 3, and 4 have all been determined. So, in these nodes now from the permanent set. So next, we will repeat the process of determining the nodes directly connected to the permanent set of nodes. These directly connected nodes are 5, 6, and 7 as shown in the figure. Notice in the figure that we have eliminated the branches from node 1 and 2 to node 4 because we determined that the route with the shortest time to node 4 it does not include these branches. So we can see that the branches leading to nodes 5, 6, and 7, branch 36 has the shortest cumulative time, which is 31 hours. So node 6 is added to our permanent set. This means that we have now found the shortest routes to node 1, 2, 3, and 4, and 6. So we will now repeat the process so we can now observe the nodes directly connected to our permanent set are nodes 5 and 7 as shown in the figure. So of the branches leading from the permanent set nodes to nodes 5 and 7, branch 45 has the shortest cumulative time of 38 hours. So node 5 joins the permanent set. So the only remaining node directly connected to the permanent set is node 7 as shown in the figure. Of the 3 branches connected to node 7 to the permanent set, branch 47 has the shortest time, which is 43 hours. So thus node 7 joins the permanent set. So this is now the routes from the shortest time from the origin nodes that will connect to the other connected nodes.